So now I'll go into detail about how we get the expressions for the grand canonical ensemble. So we've got a system here that I've already drawn, that I showed in the previous section, which is a reservoir plus our main system, and the reservoir, I'll name that R, plus the main system S. It's closed and isolated, so it's in the microcanonical ensemble. And what we're looking for is the probability of a particular microstate in the system S. So we're looking for the probability of one particular microstate, let's call it S1, with, yes, and this is in the system S, and this particular microstate should have the energy epsilon 1 and number of particles n1. So, and since this is there is only one such microstate in with this particular energy, and this is a particular microstate S1. This means that omega, the multiplicity in system S with epsilon 1 and n1 equals 1. But in the large system there are many states that are compatible with this. So in the reservoir, many states are compatible with this microstate S1. So we will call them the microstates S. Many microstates are compatible with S1, and the energies, well, I've got to write that it's a microcanonical system where the total energy is constant, and it's a sum of the reservoir energy and the energy in the energy in this system. And the number of particle is constant, and it is the sum of the number of particles in the reservoir plus the number of particles in the system. So the energies, the energy in the reservoir, it's a big reservoir, but it is one particular macroscopic energy of the reservoir that corresponds to the total energy minus the energy of the system, and the number of particles in the reservoir equals the total number minus the number of particles in the system. So we want to find the multiplicity in this of the reservoir of given the state S1 in the system. Now we know that, or we have defined that this small system, it is very small compared to the reservoir. So it means that epsilon s is much smaller than ER, and that ns is much smaller than the number of particles in the reservoir. So because the deviations are small, meaning that epsilon 1 over ER is much smaller than 1, and N1 over NR is much smaller than 1, then we can Taylor expand. Expand the state in the reservoir system around around N and R, N and epsilon. N and total energy. Sorry. So we know that we can use the Boltzmann definition of the entropy in order to work with logarithms instead. So we know that the logarithm of omega r S1 is the entropy of the reservoir, and we are now interested in, well, what is the entropy at n minus n1 and E minus epsilon 1. And as I said, we'll do a Taylor expansion, so we'll do that around around n and E, and this will give us n1 times the partial derivative of the entropy with respect to the number of particles in the system at constant energy and volume, because this is a microcanonical ensemble, so it's the number of particles, energy and volume that are constant, and then minus the epsilon 1 times the derivative of the entropy with respect to the energy of the system, keeping number of particles and volume constant. Now, these two partial derivatives we already know what they are. So we've already seen expressions for them. So the derivative with respect to the number of particles at constant energy and volume, that's minus the chemical potential of the reservoir divided by the temperature of the reservoir. And the derivative of the entropy with respect to the energy of the reservoir at constant number of particles and volume, that's 1 over the temperature. That's the definition of the temperature that we started off with. So if we put this in, we get that the logarithm of the multiplicity of the reservoir can be expressed as the entropy of the total reservoir for N and E plus N1 times the chemical potential of the reservoir over the temperature of the reservoir minus the energy epsilon 1 over the temperature of the reservoir. So we see that if we exponentiate both sides now, we get the multiplicity equals some constant times the exponential of N1 times the chemical potential of the reservoir minus the energy state in the system divided by kT, where C is just a constant. Now this starts to look like something we're interested in. So from this we can calculate, we can get the probability of the state N1 epsilon 1. Well, then we have to multiply the probabilities of the multiplicities of the reservoir with the multiplicity of the state and divide by the sum of the multiplicities of the same. And since the multiplicity of in the system itself is just 1, then we get this is some other constant times e to the n1 mu r minus epsilon 1 over ktr. Now in equilibrium, as I started off with today, we know that the chemical potential in the reservoir has to equal the chemical potential of the system, which is just the chemical potential of total, and the temperature of the reservoir and the temperature of the system have to be the same, and we just call that T. So we can now say that the probability of N1 and epsilon 1 equals this constant e to the let's just simplify a little, and instead of using these subscripts, the probability of having some number of particles in the system and some energy in the system will be the number of particles times the chemical potential minus the energy in the system over kT. And as before, we can use the normalization of the probability, and so that this means that if we sum over all number of particles, well, let's just keep these for the time being so we won't confuse them, and sum over all energies, then so we sum all the probabilities, so that's N1 times the chemical potential minus epsilon 1 over KT, which will give us which gives us this constant, which we will call the gibbs sum, which well, and the gibbs sum is then a function of both chemical potential, volume, and temperature, where we've summed over n1, or we sum over all number of particles, energies, e to the n mu minus epsilon over kt, and the probability we will continue to write it as 1 over the gibbs sum and times the Gibbs factor, which is what we call this exponential factor, just like we called the factor with just the energy over kT, the Boltzmann factor. So this is the Gibbs sum, and yes, and this part is what we call the Gibbs factor. Now, just like for other ensembles, averages are always defined the same way. Averages in a distribution can always be written as the average of this this quantity times the probability, so ni epsilon I times the probability of ni epsilon I, and then summed over all possible states. So, for example, the average particle number is 1 over the Gibbs sum times the sum over all i's ni times e to the ni mu minus epsilon over kt. And then we can use the same trick as before, that's n e to the n mu minus epsilon over kt can be written as the derivative with respect to mu of the same Gibbs factor, and mu minus epsilon over kt, because when we take the derivative here, then we get the n which goes down, and so we get n up front here. And so using this trick, we can then write the number of particles as kt times the Gibbs sum, over the Gibbs sum times the derivative of the Gibbs sum with respect to the chemical potential. And this can also be written as kt of the derivative of the logarithm of the Gibbs sum with respect to the chemical potential. And so this is the here we see it's once again it's about the chemical potential and the number of particles, and this is the central derivative and average that we get in the grand canonical ensemble.